In the rest of this chapter on locational marginal pricing, we'll cover several additional topics. First, contingency constraints. In the formulation so far, we've implicitly been considering limits on pre-contingency flow. However, most transmission systems are contingency constrained. That, for example, the binding constraint is on a limiting post-contingency power flow that would occur on contingency of another line. Sometimes post-contingency constraints are due to voltage as well. But in the typical case, we need to consider the flows in the post-contingency case that result from the generation injections and the post-contingency network. These contingency constraints can also be considered in our formulation, but they require us to use outage shift factors, so-called outage shift factors, instead of the pre-contingency shift factors that we've been considering so far. Outage shift factors evaluate the fraction of post-contingency flow on a line due to the injection at generation and withdrawal at the price reference bus. So let's see an example to see how this works. I'm going to, in fact, modify our previous system so that it has 8 lines and 4 buses. And now what we're going to think about is being secure with respect to all single contingencies. There are 8 lines. Any one of them could fail, could be outaged, and so we need to operate the system so that for any of the outages, the flows on the remaining system would be within limits. As I said, there are 8 possible single element contingencies. Let's consider an outage of one of the lines joining buses 2 to 3 as an example. This would yield the system shown in the figure, and we can analyze the contingency constraints by calculating the shift factors for this outage system. So the shift factors for this system are the outage shift factors. And in particular, we could consider the shift factors to the remaining line that joins bus 2 to bus 3. Well, it turns out, because of the way I chose the impedances and the ratings, a contingency on one of the lines joining bus 2 to 3 is the most binding contingency, and the corresponding post-contingency system happens to have the same admittances and total capacities on each corridor as we considered previously in the pre-contingency case. In other words, we can reuse the shift factors. In general, you'd have to calculate them for the post-contingency case. But here, for this system to be secure with respect to a contingency on one of the lines joining bus 2 to 3, we'd need to operate so that this contingency would not result in an overload of the remaining lines post-contingency. If we assume the same offers as previously and note that the other lines have very much greater ratings, so the corresponding post-contingency constraints are not binding for outages of other lines besides one of the lines on the corridor from 2 to 3, what we find is that the resulting optimal dispatch and LNPs are the same as the solution we found for the pre-contingency case. However, we need to understand that the pre-contingency flows resulting from this dispatch are different to the solution we found previously. The dispatch condition applied to the pre-contingency system has all of the lines in service. We must dispatch so that pre-contingency flows are within the constraints, but unless the contingency actually occurs, the flows will be due to the generation injections and the pre-contingency network. Indeed, the pre-contingency flows are typically well below the capacities of the network. So in particular, if we consider our dispatch to be secure with respect to the contingency of either one of the 2 lines on the 2 to 3 corridor, we would find that the actual flows on the lines pre-contingency, in the typical event that the contingency isn't occurring, is rather different, and generally speaking, on the binding limit, lower than the flow calculated for the post-contingency case. So in particular, on each of these lines joining 2 to 3, the flow on the line is only 187.5 megawatts, which is well below the 300 megawatt limit. The total flow on this corridor happens to be 375 megawatts, which is a little bit higher than the post-contingency flow. So the post-contingency flows in the system must be represented in terms of the generation levels pre-contingency in order to represent contingency constraints. So the relevant system constraint is on post-contingency flows. Interestingly, in the ERCOT zonal system, the commercially significant constraints were represented by their effect on pre-contingency flows on the CSCs as a function of generation. Indeed, in the ERCOT zonal system, as with our small example, the pre- and post-contingency shift factors are different, so the approximation used in the ERCOT zonal system used the incorrect derivative of the function representing the post-contingency flows in the system constraints in terms of the generation injections. In other words, the wrong shift factors were used. And as discussed previously, this tended to distort the incentives away from inducing the behavior that would have been consistent with contingency-constrained economic dispatch. Of course, generators that are trying to optimize their profits could be expected to behave consistently with their incentives. These might typically be inconsistent with the actual constraints, which then forced ERCOT to do one of two things: either adjust the constraints or take out-of-market actions to maintain feasibility. In the nodal system, the contingency constraints are represented in terms of linearizations of post-contingency flows in terms of the pre-contingency injections, so the incentives for generators are better aligned with the actual transmission constraints. There's two reasons for this. First of all, the nodal system represents more of the constraints, but also because the contingency constraints are represented correctly, as I've highlighted in the last few slides. Next topic is reactive power prices. In principle, we can just consider reactive power in our dispatch formulation. So I'll go back to the AC power formulation where we had real power balance, reactive power balance, box constraints, upper and lower bound constraints on the generations, and flow limits, which I'll represent in terms of real power flows. So we'll now also explicitly allow the cost and indeed the offer for generator K to be a function of both the real and the reactive power. So in here I've got XK instead of just PK, and XK now is PKQK, the real and reactive power generations. We'll neglect other ancillary services for simplicity, and we'll also assume that our inequality flow constraints are still on real power, although a more general representation would include reactive power limits as well. So we can solve that problem in principle and find a minimizer of it, P star, Q star, theta star minus rho, U star, and let lambda star PK, lambda star QK be the Lagrange multipliers on real and reactive power balance at generator K. As previously, we can write down the pricing rule for generator K. It's simply that a vector of prices should be given by the Lagrange multipliers on real power balance and on reactive power balance at bus K. So they're prices for both real and reactive power, and the payment to generator K would be this price vector transpose times the production. In other words, the price for real power times the real power production plus the price for reactive power times the reactive power production. So the generator would be paid on the basis of both its real and reactive power production. You might think about which is likely to be the larger price. Although this theoretical development of prices is quite straightforward, a difficulty with setting up a market is that reactive power doesn't travel very far, so that there are serious issues with geographical market power. Furthermore, solving a full AC formulation in general, which is convex, is a difficult problem to solve in real time. And furthermore, although the real power reserves, we've discussed those previously, spinning and other reserves, are typically less valuable than energy, reactive reserves, as it happens, may be more valuable than steady-state reactive power. So although I haven't formulated it, contingency constraints should be explicitly represented in such a formulation. Next topic is loss prices. Again, we'll go back to our real and reactive upper and lower limits for generation and power flow limits, but we'll simplify this a little bit. We're going to omit the reactive power flow equations. We'll omit the other ancillary services. Let's delete reactive power and voltage magnitudes from the decision vector, and we'll fix the voltage magnitude schedule at U0. This is not essential for the loss price derivation, but will simplify our development. We're going to keep the nonlinear real power flow equations explicit, however, so now we'll have a decision vector that consists of the real power generations and the unknown angles. We've gone back to considering costs that depend only on the real power injections. Let the minimizer be P star and theta star minus rho, and let's assume we can find Lagrange multipliers, lambda star and mu star on the system equality and inequality constraints. The equality constraints are power balance at each bus. The inequality constraints are the flow limits. Since our decision variable is now simply the real power generation, as previously we can write down the pricing rule. Pi pk is simply lambda k star, the Lagrange multiplier on power balance. And but to understand this more clearly, we're going to modify the formulation to eliminate the angles. To do that, we're going to make a transformation. It's kind of similar to what we did when we eliminated the angles to formulate the DC power flow equations, although we didn't describe it like this. We're going to first define an invertible matrix. I'll call it M. It consists of a single entry 1 followed by a row of 1s. Underneath the single entry 1 is a 0 vector. To the right of the 0 vector and below the 1s is going to be the identity matrix. You can check that it's invertible. So we're going to take the power balance equations, which in general apply to all of the buses in the system, including the price reference bus. By the way, I'll assume that the first bus in my vector is the price reference bus. I'm going to pre-multiply on the left by m each of the terms. That doesn't change the equations. But when I multiply m into p, I get 1 transpose p, where now 1 consists of this 1 together with the shorter vector 1 transposed. Similarly, minus p equals minus 1 transpose d over line. That's the effect of the first row of m. Then the second block row of m has the effect of picking out all of the entries of P, capital P and D that correspond to the price reference or slack bus. In other words, it pulls out P minus sigma, capital P minus sigma, and minus D minus sigma. So just rewriting the second row in terms of the first and second blocks of M, we now get 2 sets of constraints. One of them, notice, is power balance with an additional term compared to what we've seen before that represents the losses, and then a term that looks quite similar to what we saw before in the DC power flow formulation. So the AC power flow is equivalent to satisfying this first single constraint together with these other constraints. As I just indicated, this equality requires that generation equal demand plus this term. This term is the net injection of the transmission system. We've met it before, but mostly it's been equal to 0. It's the total losses in the system. In other words, this is power balance for the lossy system. So how does that help us? Well, to see how those equations help us, I want to ask a question. What does power flow software calculate? Well, typically we give power flow software a set of generations at every bus except the slack bus, and a set of demands at every bus except the slack bus. And the power flow software tells us the corresponding angle, theta minus rho, and of course the voltages that solve the power flow equations. Remember, we are using a power flow formulation where the voltages are all controlled to be 1. In other words, all of the buses are PV buses. So for us, power flow software gives us a solution of angle and voltage given real power injections at the generations and demands. We could say that it inverts these equations, these power flow equations, to solve for the angle theta minus rho, effectively as a function of P minus sigma. For different values of P minus sigma, when we run power flow, it tells us the angles. That is, power flow software implicitly defines an inverse function. Let me call it theta hat minus rho to P minus sigma. What does theta hat minus rho do? It says, give me a real power injection and I will solve for you the angles. Let's assume that the demands are fixed for the moment and assume that the only thing we're varying is the real power injections. We can think of power flow software as taking the real power injections everywhere except at the slack bus and returning the angles. Of course, it also tells us the generation at the slack bus. So for all P minus sigmas, for all choices P minus sigma, that function given by what power flow software does for us, if we plugged it into our equations, it would verify or satisfy our equations. In other words, we can use theta hat minus rho to substitute for the unknown angles according to theta minus rho is equal to theta hat minus rho, which is a function of P minus sigma. So let me now define a loss function, L of P minus sigma. It's just given by evaluating the losses. How do I evaluate the losses in terms of P? Well, I know the voltages, but I need to figure out the angles. How do I figure out the angles? I use power flow software given P minus sigma to evaluate theta hat minus sigma. And finally, I'm going to define a function G hat that will enforce power balance. It'll be the sum of the loss function minus the real power injections plus the real power demands. And if I require G hat of P to be equal to 0, then we'll be requiring that generation equals demand plus losses. Notice that if I calculate the derivative of G hat with respect to PK, what I find is that G hat by the PK, if K is the price reference bus, there's no term here that depends on P sigma, but I will pull out minus 1 times P sigma. If K is not the price reference bus, then I get the term here due to PK, but I also get the term that is due to dL by the PK, which we could, in principle, evaluate as dL through the chain rule in terms of P and then in terms of theta hat. We can also define a function h hat and a vector h overline by plugging the angles into the PLK functions and define h hat of LK of P to be the flow that results from P minus sigma. And if we require h hat of P is less than h overline, we have satisfied the system inequality constraints. So this means we can formulate our offer-based economic dispatch problem in our AC form, where we've got the costs, they depend only on the PKs given our simplifications, and in terms of equality constraints, this in fact is a single equality constraint, and inequality constraints. We can calculate the minimizer, let's call it P star, let P star minus sigma be the subvector corresponding to omitting the price reference bus, and let's assume that we can find Lagrange multipliers lambda hat star on the single equality constraint and mu hat star on the inequality constraints on all the line flow limits. As previously, we can write down the pricing rule for generator K. Pi pk is minus the G hat by the pk evaluated at the optimizer, transposed into lambda hat star, minus the H hat by the pk evaluated at P star, again transposed and multiplied into mu hat star. The G by the pk only has one entry, and indeed we've already evaluated it. If it is the price reference bus, it gives us minus 1, so we have minus times minus 1, which gives us 1 times lambda hat. There is no entry, the partial derivative of H hat with respect to the price reference bus, generation at the price reference bus is 0, so there's no corresponding entry. However, if we're not at the price reference bus, then this derivative is given by dl by the pk minus 1, so taking minus of it, we get 1 minus dl by the pk evaluated at P star minus sigma, multiplied into lambda hat star, and then minus dh hat by the pk multiplied into mu hat star. As previously, these prices must match the corresponding prices from the formulation with angles explicitly represented. So we have that lambda star k, the Lagrange multipliers that we met before, are as follows. They're given by lambda hat star, which is the LMP at the price reference bus, if we're at the price reference bus. And if we're not at the price reference bus, we have a term that is equal to the LMP at the price reference bus, that's due to 1 times lambda hat star, minus a loss penalty for the effect on marginal losses, minus a weighted sum of the Lagrange multipliers on the line flow limit constraints. The weights, in other words, the entries in dH by dpk, are derivatives of flows, that is to say, they are incremental shift factors to the constraints. They are rates of change of flows with injections. Remember, shift factors, when we did the DC power flow approximation, were changes with changes in flow. But in the AC case, when we have changing effects, changing derivatives, then we should think of these as the incremental shift factors. And of course, if we are limited by outage conditions, it should be incremental outage shift factors. The LMP at the price reference bus, the effect of marginal losses, and the Lagrange multipliers on the line flow limit constraints will each depend on the location of the price reference bus. However, when we combine them into the LMP at the bus, it will be independent of the choice of location of the price reference bus. Again, assuming we calculate to exactly if we make approximations in some or other of our calculations, such as an approximation of the losses or the constraints, then we may find that the error in the approximation is an artifact of the choice of the price reference bus. But underlying it, the ideal LMPs are, as previously, independent of the choice of location of the price reference bus. Let's see an example. We're going to revisit the one-line, two-bus example from section 9.5. We're going to consider losses. Rho equal 1 will be the angle reference bus, so the unknown angle is theta 2 at bus 2. Bus sigma equal 2 is the slack bus or price reference bus, so we will be writing down the flows on this line in terms of the injection at bus 1. However, there are generators at both buses 1 and 2, and there is demand D2 over the line at bus 2. The offers are specified for all as follows. For all generations between 0 and 200, the offer of generator 1 equal to its marginal cost is $25 a megawatt hour, as we've seen before. The offer of generator 2 is $35 a megawatt hour. So we'll have a similar circumstance to before, that when we need to operate generator 2, between its limits, it will be marginal. When we don't need to operate generator 2, generator 1 will be marginal. The key difference, however, will be now that we have losses, there will in general be a price difference between buses 1 and 2, even when the transmission constraint is not binding. So let's modify the line admittance compared to the previous case to include losses. The Y12 entry will be 100 minus 1,000 square root of minus 1. The bus admittance matrix, as always, the diagonal entries are the admittances connected to the corresponding buses. The off-diagonal entries are minus the admittance joining the bus. We'll assume that the voltage magnitudes are maintained equal to 1 per unit, so U0 is a vector of 1s. We'll also assume that thermal capacity constraints are expressed in terms of maximum current magnitude. We've met constraints previously in terms of real power, but let's shake things up a little bit by considering current magnitude. For voltages equal to 1 per unit, the previous 100 megawatt constraint becomes a 100 per unit current constraint, and there is really a constraint on flow at the end of each line. Since we've ignored shunt elements, the current is the same at both ends of the line, so we could consider the current at either end of the line, or indeed at any point on the line. The current I1 flowing from bus 1 into the line is I1 is A11V1 plus A12V2, where A is the bus admittance matrix, and we already know that the entries. We can evaluate the current as the admittance times V1 minus V2. We can therefore evaluate the magnitude of the current by taking the magnitude of this expression. That's given by the square. The square of the magnitude of the current is the square of the magnitude of the admittance times V1 minus V2 all squared. We can, with a bit of simplification, write this out as constant times 1 minus cos of theta 2 plus sine theta 2 times square root of minus 1. And with a little bit of reorganization, we can evaluate that as 2 minus 2 cos theta 2. If we require the magnitude of the current to be less than 100, this requires theta 2 to be greater than or equal to minus 0.0995 radians. Let me call that theta underline 2. By the way, it's very close to the limit of minus 0.1 radian we found in the lossless case. Using the expression for real power injection, we'd obtain that P1 of theta 2 is given by this, and evaluating it at the flow, at the angle corresponding to maximum injection, we get 99.87 megawatts. The flow at the 2 end corresponding to theta 2 is given by this expression, and again plugging in the maximum flow according to the transmission constraints would give us P2 is equal to minus 98.88. That's telling us that at that condition, at that angle condition of theta 2 underline equals minus 0.0995 radians, we find that 99.87 megawatts is injected at end 1, and we get out 98.88 megawatts. We could say that minus 98.88 megawatts is injected, or putting it more simply, 98.88 megawatts is delivered to bus 2. The losses are given by the sum of P1 and P2, and adding these together we get 0.99 megawatts when the line flow is capacity. Notice that the losses are about 1%. The injected power at bus 1 is less than 100 megawatts, since some reactive power is injected into the line to maintain the voltage equal to 1 per unit. If the demand is less than 98.88 megawatts, then we only need generator 1 to be dispatched to meet demand. The Lagrange multiplier on the line flow constraint would be 0. The LMP at bus 1 would be $25 per megawatt hour, reflecting the offer at bus 1 since it's marginal. And the generation at bus 1 would be slightly more than the demand. The LMP at bus 2 would be slightly more than $25 per megawatt hour, reflecting the marginal impact of losses to transmit power from bus 1 to bus 2. In particular, lambda 2 star would be equal to lambda hat star, which would be equal to lambda 1 star divided by 1 minus the loss factor. And since the loss factor in this case would be between 0 and 1, this would produce an LMP at bus 2 that's strictly larger than the LMP at bus 1. Not much larger because the losses are not very huge. If, on the other hand, the demand is greater than 98.88 megawatts at bus 2, then both generator 1 and generator 2 would be dispatched. The Lagrange multiplier in the line flow constraint now would be strictly greater than 0. The LMP at bus 1 would still be $25 per megawatt hour, reflecting the offer at bus 1, and we'd ask the generator at bus 1 to produce 99.87 megawatts. We'd still have 98.88 megawatts delivered at the other end. Consequently, the generator at the other end would generate the difference. The generation at bus 2 would be D over line 2 minus 98.88 megawatts. And since this generator at bus 2 would now be marginal, we would find that the LMP at bus 2 would be $35 per megawatt hour. We would have a difference in LMPs at the ends of the lines that's due to both losses and congestion. So we can see that lambda 1 star is equal to 1 minus dL by dP, P star lambda 2 star minus dH by dP1 mu over line. Let me rewrite this a little bit, pulling out the lambda 2 star, that's the LMP at bus 2 end, but also it's equal to a lambda hat star, the LMP on the system constraint, since bus 2 is the price reference bus. I can think of the price at bus 1 to be the price at bus 2 minus these terms. Notice dl by dp1 is positive, the price is positive, dh by dp1 is positive, and mu is positive, so all of the terms in the large square brackets are positive. We're subtracting them from the LMP at bus 2 in order to evaluate the LMP at bus 1, so the LMP at bus 2 is lower than the LMP at bus 1. And indeed, we know that the LMP at bus 1 is 25 and the LMP at bus 2 is 35. The losses are typically well approximated by a convex quadratic function of injections so that G is a convex function. This implies that the marginal losses are approximately double the average losses. Similarly, the thermal line flow limit constraints in H are typically convex for small enough angle differences across the lines. So from the pricing and uplift theorem 8.3 for convex nonlinear system constraints, there will be a surplus. So if we assume that the thermal constraints are the only binding constraints, pricing that includes the marginal losses will tend to generate a surplus for the ISO. That surplus could in principle be dispersed back to market participants. Let's look a bit more generally at decomposition approaches to solving power flow. We've already seen and discussed inverting the power flow equations. In general, we can't explicitly invert the power flow equations, but as in the discussion of losses, for a given choice of generations, we can use the power flow software to calculate the power flows, the sensitivity of power flows to generation, the losses, and the sensitivity of losses to generation. We can also solve contingency power flows for each contingency to evaluate for given pre-contingency generations the contingency power flows and the sensitivity of the contingency power flows to the generation. So power flow software can yield for us the information that we need to evaluate the functions G and H and to evaluate their derivatives. So this suggests an approach to solving the general AC OPF and coming up with prices. Using the power flows and sensitivities from power flow equations, from the power flow solution, we can approximate the losses with a first-order Taylor approximation about the given generations. We can also approximate each pre-contingency line flow constraint and each post-contingency line flow constraint by its first-order Taylor approximation about the given choice of generations. And we can indeed also linearize other types of constraints. We can then use those sensitivities to produce linear approximations to the true constraints that we can then use a linear programming-based offer-based optimal power flow approximation to come up with new generations. The new generations are then used to update the power flow, resolve the power flow, refine the flows and the sensitivities, and then bring those approximations back into a linear programming formulation. So we can effectively solve the AC offer-based optimal power flow by iterating between solving the power flow and optimizing the linearized approximation. We can successively linearize the power flow solution at each solution of the optimized linear approximation. Of course, all of this relies on the AC power flow having nice enough properties that such a successive linearization leads us to a useful solution of the original AC problem. Indeed, voltage and reactive power constraints require solution of AC power flow, including reactive power, and linearizing those voltage constraints could yield a proxy thermal limit, but because the voltage to real power relationship is quite nonlinear, the linearization will tend to change significantly each iteration. This is particularly true for contingency constraints. And furthermore, those voltage constraints can define a non-convex feasible set. So this can present problems with our basic notion of linearization. And indeed, recent work on OPF using a rectangular representation may allow for more effective modeling of such constraints. Pushing even further, we could imagine modeling transient and dynamic stability constraints. However, we can, supposing that the linearized iteration has works reasonably well, we can consider that approach. it's used in practice to solve any large-scale optimal power flow program, whether or not the problem has AC power flow constraints, and it proceeds as follows. We set an initial list of indices of binding constraints. We could call that the working set to be empty. We set initial linearization of losses to 0. We solve offer-based optimal power flow for the optimal generations given the current loss linearization and the current set of linearized constraints. We then take those generations and use them as input to the power flow problem. We solve for the power flow and contingency power flows given the generations from step 3. We update the linearization of losses for each binding or violated pre-contingency constraint or post-contingency constraint, and maybe even some constraints that are close to limits. We form the first-order Taylor approximation to the constraint in terms of the generations and include the index of the constraint in our working set W. If there are violated constraints or there's a change from the previous solution, we then go back to step 3 with our updated set of constraints. Otherwise, we end. And that approach can be used to, in principle, solve for an AC power flow, offer-based AC power flow. Again, we need to caveat that by observing that since the AC power flow is a non-linear, non-convex problem, successive linearization type approaches may fail badly in the case of a sufficiently poorly behaved non-convex problem. So this decomposition, however, can be used even in the case of DC power flow to avoid explicitly representing all of the line flow constraints into an offer-based optimal power flow calculation. And furthermore, in a real-time market, linearization of the line flow constraints could be based on the results of state estimation that estimates the actual states of the system. So to finish, in this chapter we have considered transmission constraints. We formulated the optimal power flow problem and considered offer-based optimal power flow. We applied the previously derived pricing rule to obtain locational marginal prices. We considered properties of the locational marginal prices, and then we considered several other topics including congestion rent, prices with AC power flow, losses, and decomposition techniques.